This is the video for my neural network. This time I have quite a lot more files, but I'm not going to show all of them. Most of these were just like for testing and trying different things. We're just going to look at this temp.py file. Here I'll run it. So we see it looks like in a way similar to what you saw with the perceptron, but also with some differences. So I don't remember if I mentioned this last time, but basically the difference between a perceptron and a neural network is that the perceptron was just one neuron, but a neural network is a network of neurons. So here I made another diagram of the architecture. You see F here is the input. This time I only had one input. Then over here this is called a layer. So in total there would be 4 layers, and this is a hidden layer because it's in between the input and output. Here we have a second hidden layer where each of these hidden layers has 3 neurons. And then in this last layer, it's called the output layer, we just have 1 neuron, which is the output neuron. So last time I tried to make the perceptron figure out whether or not it is snowing based on the temperature and whether or not it is raining. This time I changed the problem to taking the temperature in Fahrenheit and then figuring out how to convert it to a temperature in Celsius. And last time the output was always 0 or 1, but here the input can be pretty much any number, and then the output will be pretty much any number depending on the input. So here is like the representation of the current neural network. This like its brain is composed of all these numbers. Let's try to fit this. Okay, hopefully you can see that. Each of these numbers here represents another layer. So 0, 1, 2, 3 is these 4 layers. This is 0, 1, 2, and 3. For 0, it shows A0, and then it just writes input neuron. So these A values represent the activation. So that's like what value is at that neuron. And here for the input, the value is 0, which means for this example, the temperature is 0 Fahrenheit, 0 degrees Fahrenheit. And then this one is just an input neuron, so that's all it says. On here for 1, that's this layer, you can see it also has 0, 1, and 2, which is like the 3 neurons in this layer. So 0 is this one, 1 is this one, and then 2 is that one. And for each of these it shows their activation. So all of these also got set to 0. And you can see the whole entire network was set to 0, which made the output 0. But also these have a B, which is the bias. Last time the bias was like another input, but this time I just had each neuron have its own associated bias, which is like kept with it. So this neuron up here has a bias of 0.3986 and so on. And for example, this one over here, this would be layer 0, 1, 2 and neuron 0, 1. So 2 and 1 right here, its bias would be this 0.019 and so on number. Then for W, this is the weights. So if you remember, the weight represented the strength of the connection between 2 neurons, or like an input in a neuron. So in here, they have different numbers of weights, where it shows, this number shows like which neuron it's connected to from the previous layer. So for this one, it just has 0 and then this, which means the 0th neuron from the previous layer connected to this neuron, which is the 0th layer of the first layer, has this weight. So that would be this right here, because this is the 0th neuron, this is the 0th neuron, this is the 0th layer, this is the first layer. Then for these over here, you can see they have 3 numbers, because so this is 2, that's this one, because each of these neurons right here is connected to 3 other neurons from the back. So this, this, and this, this, and this, and then this, and this. As opposed to these, which are each only connected to 1 neuron from the back. That's why they only have 1 weight associated with them here. So for example, on layer 2, on neuron 1, we have, for 2, we have this, 0.34. That represents layer 2, neuron 1, and then the connection to this second neuron from the last one, which is this, because it starts from 0, so 0, 1, 2. So that's this weight right here, is 0.34. And yeah, the way the weights work is basically the same as last time. I'm not going to go through like full examples because it's a lot of calculation, but you can think about, for example, for this, we'll say like this neuron right here, it would get past the value of this multiplied by that weight plus the value of this multiplied by this weight, and then it also would get added the bias. So this neuron's value over here was 0. So hold on. This one was 0, that's up here, 0. So this one would be multiplied by this weight. That's 0 times this, plus this neuron. Oh, sorry, yeah, and it has this one as well. So it's all 3. This one would also be 0 times 0, because this neuron up here had an activation of 0. And then the third one would again be 0, because this one had an activation of 0. And then the bias would be added, which is this number. And it would look like the output, like the activation is supposed to be more than 0, it's at 0.11. But after you go through that process of getting this sum, you also plug it into what's called an activation function, which modifies the value a little bit, which is why it still ended up going to 0 at the end. And that's why all of them ended up at 0. We can see, like, on this other example where the input was 453 degrees Fahrenheit, these ended up at different ones. Like this same neuron up here, this time went up to 180 in its activation. So again, the weights and biases get tweaked with each example. You can see, like, for example, this one started at 0.69, then went to 0.331, and now it's 0.334. But this time there's the way that you calculate how these weights change is way more complicated. This time you have to use differential calculus, which I spent quite a long time learning. Basically, what you want to do is find how each of these weights and biases, how changing them will affect the performance of the entire network for that example. So like for this weight, you see whether increasing it will make the network perform slightly better or slightly worse. And in this case, it decided that decreasing the weight would make the network perform slightly better, which is why the weight was decreased to this. And how that basically works is that well, this is for this one. So you see how this would affect the sum of this, how that would affect the activation of this, how this would then affect the values of all of these activations, because each of them will be connected to this neuron. So whatever this neuron gets set to, that influences all of these other ones. And then how each of these will in turn influence the final neuron, and how that final neuron would influence the performance relative to the actual temperature conversion. And for that you use like the partial derivatives and the chain rule, which I'm not going to try to explain here. And also, since this is like a way bigger network, it's going to take a lot longer to train. So in advance, I have this other running version of it, which you can see it ran many times, 21,000 times, but eventually it got its cost down. Cost is like how poorly the network does. So the lower the cost is, the better. And you can see for the last 100 examples, it has 0 cost, so it did perfect. For the last, 10,000 examples, it was like slightly worse, and then for the last 100,000, it was again slightly worse. But this is still pretty good. It means it's like about as accurate as you would need. See, for example, on this one, the input was 436 degrees Fahrenheit, and its output was 224 degrees Fahrenheit, 0.7. So if we like look into Google, 436 Fahrenheit to Celsius, we get 224.44. So this one was off by, wait, I don't know why it's set to like 990. Well, it was off by like around what, 0.4 or so. So barely anything, especially when you compare it to the size of this number. That's like 224.4, 0.4 out of that. That's like less than 1% off. Like 0.0, or wait. Yeah, well, okay, it's like 2% off the actual value, which is pretty good. Now I can also show the code. The code is more complicated, so I'll try to be briefer with it. On here, this like generates training data, which is the examples it's going to use to run, and it basically just generates a random number from 32 to 1024. Then goes with that, and then so that it creates this like list of training data, and then it tells the network to train for that in this train batch function. That goes over here. It initializes its default cost, which will get updated as it goes. In here, it prints out the current state of the network. Okay, yeah, that makes sense. So sorry, the first time when we ran, did I change it? Okay, yeah, so see the A was 0, which didn't really make any sense, because where it's supposed to be from 32 to 1024, that's because this printed out the current state before it started training on it, so it never had a chance to properly set the first input. But after that, it does train on each example. It has this like pretty complicated function here. It first computes the value it's supposed to have. So remember how you like take all of these and like sum them, and then add the bias, have the activation function. All of that is pretty computationally expensive and would require a lot of time. So some people that are really good at math came up with a way to do it with linear algebra, which uses these things called matrices to basically store the numbers in a more efficient way and compute them in just one step. That's what happens here. Self-compute matrix, and this like creates these matrices and then uses matrix multiplication to add them quickly. Then it gets the guess that the network made, it gets the real example, gets the cost based on that. Here it starts going through every neuron and getting partial derivatives of how the cost would change based on how you would change that weight or bias, and just it records every single change that it wants to make, because it has to record multiple changes, because like imagine based on what this neuron wants, this weight would increase the cost, so it'd make it worse. Increasing this weight would increase the cost, but based on this neuron, increasing the cost would decrease, increasing the weight would decrease the cost. So if they have like conflicting requests for different changes, you have to factor that in and like change the weight depending on the strength of the requests. Like this one says it will only slightly increase the cost, but this one says it will really decrease the cost. So you listen to that one more. That gets influenced and factored in through these weight changes. Like over here, weight change, you add one. So these are all like the requests for the weight change. Finally, you run update parameters up here, which basically goes through every neuron in every layer and updates its weights based on the weight change that we wanted. Over here, that's for the weights, and then its biases you also update. So for the, based on like all the bias changes that we, yeah, here you can like change different stuff that you want, like the learning rate. That makes it like, it's basically a multiplier for how like fast it responds to requests. So generally you want that pretty low so that it doesn't end up like overshooting the request and making an incorrect change. Yeah, this is just like a data structure for the neuron, and then like for the input, and then here are all of these derivatives with like the activation function stuff, and here the ground truth. So again, this is like for educational purposes. In like a real app where you needed to where you would need to convert from Fahrenheit to Celsius, you would just like use code like this, which just uses the normal formula. So yeah, that's it basically for neural networks.